Okay, so basically what we're going to do today, we're going to finish this chapter, and hopefully we'll finish it in time. And I'm not sure exactly if Tuesday we will have a session or not. It's going to depend honestly on you guys, so we'll see. Okay, so last time, let me get the mouse in here. Oh man, I should probably turn off. No, I don't want to turn off the sound. I probably, sorry guys, okay, I'll have to figure out on how to stop this nonsense and later on, namely the notifications they're popping up. I don't know if you saw them or not. Anyway, so let me get the, from where we were last time. So last time, basically, if I remember correctly, we did Maxwell's equation in the vacuum, basically, where we said, okay, and not vacuum, I meant where we are far away from any source. We called it the free space, basically, away from any source whatsoever, namely rho is equal to 0 of charges. And also the current density also was chosen to be 0 because we are far away removed from any kind of source for electric field or magnetic field. At that point, when we solved it, we saw, okay, we're not really going to solve the general equation for x, y, z, and t because it's really mathematical complications no more. So we decided, you know what, we're going to focus on far away on the so-called plane waves, okay, planar solution. And the planar solution, then, in that case, what matters is just one direction, pick any direction you like. We look for the solution that really depends on the x direction only. So it's going to be x and t, of course, because this is a time-dependent phenomenon. In addition to that, also, the magnetic field will exhibit the same thing. So we're saying, okay, this is basically the, immediately, when we did that, as a conclusion from Maxwell's equation, both the x component for the electric field and that of the x component also for the magnetic field turn out to be 0. And we argued the case that it could, trying to get some real estate in here, okay? So basically that if the wave is traveling in one direction, the components in that direction are 0. That means that this waves, the solution to these equations is transverse waves, okay? Because it's going to oscillate in any direction other than the direction of travel. So it's going to be in the y and the z direction, but not in the x direction. So that's basically the first conclusion that we drew. Also, we said, you know what, that's too complicated. We still have 4 equations with a lot of different problems in it. So we said, okay, we're going to take, by choice, Ez to be 0. And this is the so-called polarization. So the wave is polarized in a specific direction, and that direction is the y direction. So we said, okay, we're going to take the direction of y as that of the electric field. So at that point, we have another solution that came in addition to the fact that now we know that the, I'm sorry, let me get the mouse pad. In addition to, for those who came late, I'm trying to adjust to the new computer, okay? Sorry. Anyway, the point being in here is that once we took that, we came up with another conclusion, the fact that By will turn out to be 0. So By actually was 0. So I have a bunch of zeros. So the only thing that remained at the end, of course, is Ey, the one that characterizes the polarization of the wave, and also Bz, okay, the one that is actually the only component that is left then after that for the magnetic field. It turns out, once we solve it, that they turn out to be waves. And the wave solution, we took it in the progressive direction of the, namely increasing values of the x-axis. So because if you guys remember, there is a, I'm sorry, there is a left and right waves, and we took the right traveling waves as a solution. Of course, there is another one, especially when it comes to standing waves, we are going to consider the other one traveling to the left, okay? So we took the right one. So this is basically what we said. We're going to take that as a solution, borrowing the idea from physics 1. And then it turns out that the magnetic field will have the same phase, will have the same angle. So there is no phase delay or anything like that in this case. So that also has a cosine of kx minus omega t. And so this is BZ now. But the value here, the maximum, turned out to be just of the electric field divided by the speed of light c, where c turned out to be related to those epsilon naught and mu naught. C was a quantity 1 over square root of mu naught epsilon naught. This came from the wave equation. And also this k and omega are not completely independent of one another. They are related through the so-called dispersion law. K is equal to omega over c, or omega is equal to kc, or if you like, in terms of frequency and wavelength, lambda times the frequency is equal to c. It's the same relationship. Basically, it's all coming from Maxwell's equation. This is what we have seen so far. This is everything we did last time. Okay. So now the challenge is the following. We want to calculate the energy. Okay. So we want to find the energy associated with this wave. Because this is a wave now. We know it's a wave. Sorry about this sound thing in here, okay? So remember, and I don't know if Sophia is here or not. Let me check quickly here. Okay, she's here. Good. Because that discussion we had a long time ago, and the energy density for the electric field, when we said that if I have an electric field, what I really do have in this case, I have a bundle of energy. I have an energy that is proportional to the square of the electric field, the square. So in this case, it's 1/2 times epsilon naught. Epsilon naught always appears down in the denominator, except in the energy density, it appears in the numerator. And so this is basically the energy density. Remember, the unit for this one is not joules, but joules per cubic meter. Okay? So this is an energy per unit volume. And also, when we did the magnetic field, also we arrived to a similar expression for the magnetic field. The energy density there, it turns out to be 1/2 mu naught. Everywhere we did magnetic field, the mu naught was in the numerator, except when it came to the energy density, it also went downstairs. So they flip roles in here when it comes to the energy. Proportional also to the square of the magnetic field. So again, the unit for this guy is also joules per cubic meter. It goes to reason then that the energy, because all I have now is an electric field and a magnetic field, that the energy for the entire electromagnetic field now is going to be the EM, just the sum of the two. Okay, so just add the two when you're done. So let's calculate this quantity and see how much it's going to be equal to. So the energy for the electromagnetic wave now is going to be equal to, first of all, 1/2 times epsilon naught times E squared. E squared is E max squared times cosine squared. So it's E max squared times cosine squared of that argument, cosine of kx minus omega t. Plus, this one is 1/2 divided by mu naught. So I'm going to put mu naught in the denominator. And times the intensity squared of the electric field. I'm going to express everything right now in terms of the electric field. So it's going to be E max squared over C squared. And the same argument, the same cosine squared of kx minus omega t. So this is the instantaneous value at a given time and a given point in space, x and t, of the energy density. How much energy I have for the entire electromagnetic wave per unit volume, basically, per cubic meter. So I'm going to sub this expression immediately for C squared. Remember, C squared is 1/mu naught epsilon naught. So because C is 1 over the square root of that number. So if I do that, I have it in the denominator here already. I have 1/c squared. So 1/c squared actually is going to be just mu naught epsilon naught because of that relationship. It's just mu naught times epsilon naught. So I'm going to sub this expression, and this is what happened. First term, that's the electric field. I'm not going to touch that. I'm going to leave it intact. It's the magnetic field contribution that seems to be that involves c squared. So it's going to be plus 1/2. I have a mu naught in the denominator. 1 over c squared is mu naught times epsilon naught. So the numerator will have a mu naught times epsilon naught times, of course, E max squared times cos squared of kx minus omega t. As you can duly notice, the mu naught cancels. And the two terms are identical. Whether the electric field or the magnetic field, they have the same contribution in terms of the energy. When we did the intensities by themselves, we saw that the intensity of the magnetic field is 1 over c times that of the electric field. In other words, when we're doing measurements for electric fields and magnetic field for the electromagnetic phase, we focus only on the electric field because it's much easier detected, much easily detected by equipment than the magnetic field, which is too weak. However, when it comes to energy, the two have the exact same contribution, whether that of the magnetic field or that of the electric field. This one, numerically speaking, it's epsilon naught, which is a very small number, 10 to the negative 12, times E max squared, times cosine squared, times 1/2, because the mu naught cancels when you sub the value of c squared. And this one is exactly the same number. So the only thing between them is 1/2 plus, that's the whole thing, is just epsilon naught times E max squared times cosine squared of kx minus omega t. That's it. So the energy, both of them, albeit they work together basically, so the whole thing is just one thing. Both the electric field and the magnetic field, they work together when it comes to this one. Now the frequencies are extremely high. Frequencies usually, I mean, for a visible light, they're of the order of 10 to the power 12 or something like that. So this omega is very, very rapidly, very high. So that means if I wait 1 second, this is a long time. So that's why what I'm trying to say in here, we need to do an average to find these quantities. But before I do an average, let me take this following situation. I'm going to find the actual amount of energy that hits a given surface, okay, from this wave. Remember, we called it plane waves because we're looking at some point in space x. So this is the point x in space, and there is this wave. If I wait a little later time, let's say, for example, 1 second, this will move a whole distance c because it's moving with the speed c in the x direction, because that's basically what that expression is saying. So after 1 second, the front wave would have moved 300,000 kilometers, basically. That's what the speed of light is. So if this area is A, and this area is A, the distance between them, the separation between them is c times the amount of time we're waiting for it. And if that amount of time is not 1 second, it can be dt if you like, okay? So that's basically the amount of time. So if you don't like 1 second, and 1 second is too long, and you would want to wait a little less, that's fine. Then the distance the light would have traveled in that amount dt is c times dt. Now the volume in space that has basically carried with it this much. So if I'm waiting in here, in other words, and I wait an amount of time dt, there is anything that is from here, from this point in space, c times dt, all the way to where I am is going to pass by me. You guys understand that? So this is the amount of energy contained in that volume. So the amount of energy now, which I'm going to express it as E, or I think the problem with E is that we already have the electric field. So I'm going to use the letter U again, okay? So this is U, capital U. So this is the energy for the electromagnetic wave, not the energy density, the entire energy contained in that volume. Of course, it's going to be the energy density itself, which is lowercase u, em, times the volume. Can anybody tell me what the volume of this shape is? I have an area and I have the length. Any suggestions? What is the volume of this this shape, basically? Okay, I have the area already. So what do I need to do? Okay, I got your point, Tim, but I needed to express it in terms of the area, though. What do you think? Okay, and L is equal to C dt. Okay, so no, not this is not a volume winter. This is not a cube winter. Okay, this is any area. It doesn't matter. So we need to keep the area basically independent. So the volume is actually going to be. So this is not all of the energy. So this is just an energy received in a certain amount dt. So I have to be specific about this point in here, that this is actually du, because I took a volume not in 1 second. I'm considering it in any amount of time. So if I sort of follow John's argument, he's saying, okay, the area times the length, and the length I know it's c dt in here. Okay, so that's the volume. So now this term is actually in joules. This is no longer energy density. This is actually an amount of energy that I receive on that surface in a given amount of time dt. So I call power, if you guys remember from your physics one class, power is the rate at which energy is delivered per unit time. That's what power is. So the first one is in joules. This is in watts. What I want you to do today, and it's extremely important once we reach this point in here, is to keep watch for the letter P. It's going to appear 3 times today. And it's critical that you need to make a distinction between all the 3 P's. The first one is going to be P for power. The second one is going to be P for momentum. And the third one is going to be P for pressure. They're all 3 terms that are going to appear today, and there is no escaping that. So the power, and I'm going to try to make the notations a little bit slightly different so that we keep track of which one is which we're talking about. So this is a power now. It's in watts. Okay. So that's the expression for the power, is the rate at which. So it's clearly from this expression is just the energy density times the area. That's all. Because dt, and times c, I'm sorry, because dt cancels from both sides. So this is now the power as expressed, as received on that point. So basically, as the wave is coming, it's carrying with it power, and this is how much it is. So if I try to go back into that expression, we'll find that the power will be simply equal to, of course, the 1/2 is added up, so it's going to be 1 epsilon naught times E max squared times A times C times cosine of kx minus omega t squared. Obviously, this power, because the cosine function is can be positive or negative, but it's going to be like this because it's squared now. So it's going to be like this. Whether I'm looking at it in space or in time, it doesn't matter. So this axis can be t or x. So if I wait a long time ago, so if I'm at a different point in space, it's always positive, basically. And the separation between them is related to the period of the signal. So that's basically what this thing is. And here is a maximum. Here is this entire expression, basically. Okay. So it's, you're gonna call it P max or P max if you like, what I call it. Okay, so it varies from 0 to P max. Now, again, because T is so rapid, I mean, the period is so small because of the high frequencies, I can average this expression both in time and space. It doesn't matter, either in space or in time, okay, because the lambdas or in terms of the period T. The average of the cosine squared is going to be 1/2, and we have done that when we did the power, the electrical, the AC circuit. Let me quickly remind you of how that works. Cosine squared, there is a trig identity that is equal to 1 plus cosine of twice the angle divided by, that's a plus, divided by 2. So when you average this quantity, this averages to 0 over a period, and this will give you 1/2. So basically, the average is just going to be 1/2. It's going to be midway here, exactly, okay? So again, you can do the integral if you like, but the average power now is going to be just 1/2 times epsilon naught times C times area A times E max squared. Okay, squared. So again, the fact that I have an electric field, now I have power. This is how much power is hitting the area that I'm talking about in here. Okay. Now, before I go any further, I want to come back to this expression for the power and play with it a little bit. And I will tell you exactly what I mean by that, okay? Or actually, let's go to an easier expression, namely for the energy density. It doesn't matter which one is which, because I have this Emax squared that I want to express in 3 different ways. First of all, instead of expressing it in terms of the electric field, I can express it in terms of the magnetic field. Because remember, Bmax is simply equal to Emax over C. We have seen that last time. So instead of expressing the energy density in terms of this term, so if I have Emax squared, everywhere I have Emax squared, I'm going to just say it's actually C squared times Bmax squared. Okay? Well, if I can do that, then that all requires from me is just divide by mu naught epsilon naught, because that's exactly what Bmax squared, what C squared is, times Bmax squared. That's one way of doing it, okay? I can express that entire expression that way. There is another way that I can express Emax squared, and this is what the one I'm going to adopt actually right now. It's Emax squared is actually, I'm going to think it's Emax times Emax, and Emax is Emax, but the other Emax, I'm going to express it as just Bmax over, Bmax times C. Okay? So both of them are Emax squared. This has the advantage of writing this expression in the following way, expressing it with the due fact that it's not an Emax squared by itself, it's not a Bmax squared. This wave has both of them in place. So this is 1 of square root of mu naught epsilon naught times Emax Bmax. I want to emphasize on this point in here with the fact that this is actually both the electric field and the magnetic field at work. And there is another advantage actually for writing it this way. So let's go back to the power now, since we are ready to do that. So we're going to write the instantaneous power. The instantaneous power involves the following. Involves first of all epsilon naught times C times A times E max squared. But Emax squared, it's an Emax times Bmax times 1 over square root, which is actually another C, by the way, okay? That's all, okay? Times the cosine squared. Times the cosine squared of kx minus omega t. So I have a C squared. I have a C squared, which is just 1 over mu naught epsilon naught. And that epsilon naught will cancel the epsilon naught, and the entire expression now can be written as, so C squared, I'm subbing it, so this C and that C are actually C squared, which is just 1 over mu naught epsilon naught. This epsilon naught and that epsilon naught will cancel, so this entire expression then boils down to the following. Emax Bmax over mu naught, okay, times the area times cosine squared of kx minus omega t. So I just rewrote the expression, that's all, for the instantaneous power in terms of just electric field and magnetic field. This combination of the two is worth mentioning. Let me explain why is this important, okay? If I look at this vector that is formed from the product of these two vectors, E crossed with B, divided by mu naught. So this is the cross product of the two vectors, electric field and magnetic field. It turns out, and let's do a calculation first. So this S now, which has a name actually, we're going to call it Poynting vector. This is a Y, by the way. This is not an I. This is not a mistake. When I first heard about this, I honestly thought it was a mistake, that they probably misspelled pointing because you want to point towards something, you know, like, so this is the Poynting, it's Mr. Poynting himself who invented that vector. That's why they call it after himself. But you will see exactly what it does, and it points to something, okay? So the Poynting vector points to something very important that we're going to need. So S is equal to 1 over mu naught times, again, I'm just forming the dot product, the cross product of these two vectors, that's all. So the electric field has no no x component, has a y component, and has no z component. It has also, the magnetic field has no x component, no y component, but an x component. So if I do the calculation in here, this is E max times cosine of kx minus omega t, and this is B max times cosine of omega t. It's just I'm writing them now concisely as just one component. So the x component will be E times B minus 0 times 0. So that's going to be fine. The y component, which is this one, eliminated. So you'll have 0 times B, which is 0 minus 0. So there is no y component for this vector S. The k component also has no y, because it's going to be z squared, 0 squared minus 0 times k, which is 0. So the only thing that is going to remain from this one is E times B over mu naught in the I hat direction. So again, E is E max cosine of kx minus omega t, and B is B max times cosine of omega t. So this actually vector S is exactly the magnitude of that power. I mean, its magnitude is exactly that power. Let me, of course, I have to multiply it by 8 to make it work. So S again, E max, B max over mu naught times cosine squared, because each and every one of them brings that cosine to the table, in the I hat direction. So this vector now does not point in the y direction or k direction, of course, that's the result of the cross product. So it points in the direction of travel of the wave. So, and its magnitude, if I multiply it by the area, I have found actually what the power is. So this vector P, this vector S has an important two things. First of all, the pointing vector points towards the direction of travel. As a matter of fact, you can take a wave that is traveling in the opposite direction, in the negative I hat direction, and you will find that actually S will compute also the same way. So it's always pointing to where the wave is traveling. It's not called pointing again because of it points to something, but that's exactly what it does. So that's one thing. Furthermore, the magnitude of S times A is the power. So S is the power, basically. S is the power, the instantaneous power. And if I average this quantity over X, so the area is A, okay, so that's, we're not really going to, so S by itself is no more than just P over A, the power per unit area. So the unit for it are watts per cubic meter, I mean per square meter. So that's basically what the units for this guy is. Now, if I average the quantity now, P, this is called the intensity. The intensity is the average P per unit area. So this is the intensity. In other words, the intensity is the average of the pointing vector. So it has a lot of stuff in it. It tells me the intensity of the wave. Its magnitude, actually average over time, is the intensity of this electromagnetic wave. How much radiation basically we're receiving on a given surface. That's basically what it is. And it's also related to the power. So there's a lot of things that you can, in addition to the fact it points to the wave. So the pointing vector is extremely important when you're doing electromagnetic radiation. So you really have to know how to compute it. And a lot of the problems in exams are going to depend on S. So if you have problems with it, you really have to fix those things. So the pointing vector, the definition for it is simply E cross B. Mu naught, of course. Okay, that's basically how we defined it. So it's a very, very important vector that you're going to need for doing calculations, and it tells you a lot about the wave. It tells you which way it's moving. It tells you basically the power at this point. It's going to tell me something else down the road, which we're going to need. So you're going to see that this S is extremely important when we do these calculations. So I cannot really emphasize how important it is, because we're just basically touching the surface of this guy. Now, if we measure the intensity of radiation that we receive on Earth from the sun, on average, we receive about Oh man, to do this, yeah. Sometimes this thing goes down. So let me get a thicker pen, okay, because I don't like this. Is this still the same size? Let's probably use this one. Okay, so on average, we receive on Earth about 1.4 times 10 to the power 3, or 1400 watts per square meter from the sun. So this is how much radiation we receive on the sun. That's what justifies the solar panels or the solar heating or whatever mechanism that you have to gather the energy from the sun. So if any problem tells you that, look, you have this much basically radiation, no, you have a device that is sitting on the Earth or around the Earth or anywhere around the Earth, you're talking about this number. So the intensity I is this much. That means this is how much S on average is. So if you give an area, for example, if you have a swimming pool and you want to heat it, then what you do in this case is very simple. All you have to do is just multiply this by the area of the swimming pool and you have how much energy is received per unit time. That's how many watts. So if you're trying to find this number, what do you mean solar constant? This is on the Earth. If we move away from the Earth, if we are, for example, on Mars, this number, of course, drops because Mars is further away, and this drops like 1 over distance squared from the sun. So you have to really, if we go back to, for example, Mercury, this number increases because Mercury is closer to the sun and receives more radiation. So this number depends on how far you are from the source, that's all, of the electromagnetic waves. So on Earth, this is the number. This is experimentally, and you can do it just by taking a 1 meter square bucket of water, for example, and leave it all day long and see how much temperature it rises, and that's exposed to the sun, and multiply that C times your mass times the specific heat of water and how much temperature increased, and you will see how much energy is gathered over how many hours. Divided by that, how many hours, you probably are going to find the value in here for basically the energy per unit time, which is the watts per meter squared, okay? So do you guys understand the idea? Yes? So any problem that you guys are faced with, and they tell you specifically that something is near the Earth or here earthbound or something like that, use this number for it, okay? And we're going to take an example probably down the road. Let's continue with this vector S because we have something else that is extremely important also when it comes to this phenomenon, namely the fact that, okay, if I have surface of water or anything like that, it's always subject to basically being hit constantly by radiation, so it's going to absorb energy. Now, if it reflects it back, it's going to reflect it back. So if you have a mirror, for example, or a piece of metal, for example, that is perfectly reflective, then the radiation is received, absorbed by the metal, and then bounced back. So in this case, there is a process in here, and we're trying to understand now the pressure that the wave exerts on a specific surface. So that's where the other P is coming to play, the pressure. Okay. So for the pressure, this is the way I'm going to write it. Okay, so it's going to be pressure. And the way I write pressure today is with an underscore bar, just to make the distinction between the two P's. The first P was with the plain capital P, and the second one is this P. Now, the pressure is just the force per area. Okay? That's basically what you have seen from physics 1. The pressure is force over area. Now, the force, if you guys remember again from physics 1, is the change in momentum over time. And here is the third P now. So I'm going to P with this, like I'm writing a cursive P, okay? So this is the change in momentum over time. That's what I promised will happen today. You will see 3 P's. And you have to really pay attention to your P's, otherwise you'll have problems with this class. At the end of the day, actually, in problems, the only 2 P's that remains are the pressure P and the power P. So you have to pay attention to which one is which. Most of the times we don't deal with the momentum. So this is the momentum, okay? From your class again, that the change in momentum over time is the force. That's the second law of Newton. So this is something that we know from way back. So again, this stuff is from physics 1. So let's find what this thing is for the wave. Now I'm going to take 2 cases. I'm going to take a surface that is absorbing. So a wave that is being absorbed, okay, and a surface that is reflective. So a wave hits a surface, either it bounces off or it's completely absorbed, and basically the surface is taking all of that energy that it receives from the radiation. Mr. Maxwell has shown, and I really don't want to go into the details for it, but basically if I have you can probably understand it better with quantum mechanics, but since you guys did not do that, so let's just use the result from there, that the momentum received imparted, so this is the momentum imparted by an EM wave is proportional to the energy received by that surface, by the EM wave again, and of course the speed of light c in here. So that's basically the argument that he argued. Now, if that amount of energy is completely absorbed, so that energy that we received earlier, where did I write it down? Yeah, this energy is the entire energy that the wave receives, okay? So that's basically the expression that we have to deal with in here. So that's the energy that it receives per unit, it receives, period, end of the story. So you let it explode for 5 hours, it's gonna receive that much energy, and that's the momentum, so it's being pushed basically. It's gonna be a small value, but that's basically how much it is. So that's the momentum that is imparted to the, to this surface, okay? So now if I calculate delta P over delta T, that is actually the force, and the force in this case is 1 over c times the rate at which the energy is coming, which is delta U of the electromagnetic waves over delta T. And this is again is power. So the force is going to be equal to 1 over c times power. So the force is the power P over c, okay? So that's how much force it is. And now if I'm interested in trying to find the pressure, all I have to do is, again, the pressure is equal to force over area, and the force is the pressure, the power over A times C, okay? And the pressure over A, and the pressure over A is just Poynting vector, that's all. So the power over A is a Poynting vector. So in this case, the pressure is going to be S over C. You see here how much valuable that S will turn out to be. Note the P now. This is pressure. I want to write this is in here. This part of the class is kind of confusing even when we are live, okay? When we are face to face, because I always emphasize on this thing, and sometimes it gets confused. And unfortunately, for so many long times, I think, what, 150 years since Mr. Maxwell made his arguments, we still use the same symbols for P and P and P, okay? So hopefully you guys are paying attention enough to note that this is actually a pressure. The unit for this one is actually a Pascal, okay? Because it's Newton per meter squared, okay? Versus the other P, which is watts, okay? Or joules per second, versus the other P, which is a Newton per second. Okay, I mean, yeah, Newton second. So there is, or kilogram meter per second. So there are different stuff in here as it comes to play. So this is for a surface that absorbs all the radiation. Now the surface that does not basically reflects back the energy. So in this case, it back, and then it pushes back when it's basically like an implosion in here. You have it receives the material, then you have an explosion. So in this case, it's twice the momentum in that case. So for a reflecting material, if the internet drops, probably it's going to come back again, or Zoom. Sometimes Zoom does that to me, okay? So please don't go away, okay? So again, if we have a material that does both, so basically the energy is going to be multiplied by a factor of 2 in here, that's all. So in this case, this will be a 2 here. because it's going to give energy, and then when it goes back, it's going to give back the energy to the radiation so that it bounces back. So the total change in this case is, and it's frozen. Okay, the total change will involve the value 2. So the pressure in here, the only thing that is different is that it's going to be 2s over c, and that is for a totally absorbing material. So this is absorbing, and this is reflecting. And you will have to pay attention to these two words when you're doing problems. There is a 2 in the first one. It's 2s over c or s over c. That's all. That's the only difference in here. Of course, if I'm trying to find the value that is on average, it's going to be the intensity over c, or the 2 times the intensity over c. Because again, the Poynting vector now tells me a lot. Tell me about the intensity of the wave, which way it's moving, and the pressure that is in there, and the power. So it tells me a lot of things basically as I'm working my problems. So this Poynting vector is really very important when we're doing chapter 32 in here, when we're doing electromagnetic radiation. So if you have problems with it, you really have to fix those things big time, and it's going to rely a lot on it. Now, if I have surface somewhat reflecting, somewhat absorbing, so it absorbs some and reflects some. So, and let's say, for example, R is the coefficient of reflection, then in this case, the pressure P is going to be 1 plus R times S over C. A lot of textbooks, they use letter F for fraction. Okay. What I notice also in exams, people start to confuse the F with another F, which is the frequency. So that's why I'm using the R in here, which is just how reflective it is. And it's a number that changes between 0 and 1. R changes between 0 all the way to 1. So if it's 1, that means it's completely 100% reflective. If it's 0, that means it's 100% absorbing material. Anywhere in between, it's more realistic conditions. It doesn't matter, really. What dominates this expression is S over C anyway, which is a small number. This, of course, has some interesting applications, among which, for example, is solar sailing technology that is used. I mean, yes, the pressure is small. Yes, the force is small. But over time, it's going to give you very small acceleration. But that acceleration will give you an increased value because the velocity will increase from the previous velocity, albeit the acceleration is small. But it's going to give you tremendous velocities if you are in outer space. That's why it's exploited, actually. I think there is a Japanese, a spaceship that uses this technology. Other people, they're interested in it because it's a lot cheaper to use the star actually to push your spaceship than having to have any source. And that velocity can reach tremendous speeds over time, okay? So that's basically the idea behind it. If, for example, there is an example in the book where it tells you that you have a satellite that is 4 square meters, that's its wing, 4 square meter, and it's earthbound, and they want to know how much pressure on it from the solar radiation. Well, we know how much average its S is. Its S is actually the intensity. It's 1.4 times 10 to the power 3 watts per square meter. So that's my S. And if I want to know how much pressure, all I have to do is divide that by C. Speed of light. So I know how much pressure that satellite is under from the sun. So that satellite is going to be under, the pressure is going to be what? Let's assume that it's perfectly absorbing material. So it's going to be S over C average, and the S average is 1.4 times 10 to the power 3. And this whole thing divided by 3 times 10 to the power 8, I'm sorry. And you will find that it's about 1.8 times, what is it? 1.4 divided by 3. I'm kind of not thinking to do the math in my head. Divided by 3. So it's about 4.67 times 10 to the negative 6, because when you carry the other number, so it's 4.67 times 10 to the negative 5, but there is another decimal point in here, -6 Pascal. So it's a very, very small pressure, okay? But if I want to find the force, I have the area now. So I want to find how much force this one receives. So I have to multiply just that number by 4. So the force is going to be pressure times area. So this number times 4 is going to give me a very small force now. So this number times 4, it's going to be about 1.87. 1.87 times 10 to the negative, what is it? 5, because I moved the decimal point back, Newton. So this is a very small force, very, very tiny force. But of course, over time, it's going to have a very small acceleration, but over time, it's going to have an effect on your satellite, okay? So that's the point being, albeit 4 meters squared is not really the ideal for solar sailing, but that's the point behind it, okay? You can do it also for a laser beam, okay, and see how much pressure exists on the screen. So you have the area there, and you have the radiation. You can do all of these problems, and it should not be. And you can read the intensity from the laser beam. They tell you how many watts basically it's going to deliver. So you can do that problem, and you can have you can solve all of these problems basically based on these ideas. Any questions so far? I moved, by the way, the homework assignments, and I did not want to do everything at the same time because I was afraid that you guys will leave everything and then realize you have a lot of things to submit at the same time. So I think I put one on Monday afternoon, and Monday evening, I should say, and another one on Tuesday evening, and another one, the lab, I left it where it was before so that you guys have time to work on these things. And because we're just finishing the chapter, I didn't want to also have you guys submit stuff that is due from chapter tonight, okay? So, no questions. So I'm going to continue now with something that I didn't discuss last time. And usually we don't discuss it at that point. We discuss it later. And my thing is not working. So let me see why. Come on, man. Okay, good. Let me check the attendance while I'm here at this point. Where is the print screen? Okay, never mind. Okay, so okay, we have one person who's not here. So the last point that I want to make in this one in here is that we took a wave that was traveling to the right, namely it has the phase kx minus omega t. When you took waves, you also saw that a wave can travel to the left. So you could have potentially kx plus omega t as another solution, okay? So there is another one. So those are the phase. So this is a right, and this is a left. The trouble with the left wave is the following. This equation will really flip the sign between the electric field and the magnetic field. It doesn't matter which one is which, but I'm going to take just this example in here to show you there is a problem. So I remember that Faraday's law says this. This is where we got a relationship between these guys. So it's equal to the change. Because everything else, so basically I'm going to write it in the vector form, okay? Control Z, Control Z, Control Z. So I'm going to write it in its full-fledged form, okay? So this was Faraday's law, and when we solved it actually, in the Z direction, we have minus dB over dt. This is in the Z direction because B turned out to only have a Z component, is equal to basically the only thing that is going to remain is the derivative of E, which is in the Y direction with respect to X. Well, there's a problem in here. If I took the same sign, if this was a cosine and the other one is a cosine, that negative sign will have a problem because the derivative of kx in here will have a will have a negative sign, and the derivative of the b will have a negative sign, albeit this one is multiplied by omega, the other one will be multiplied by k. It doesn't matter. Those are just positive numbers because omega is equal to kv. We don't care about that one. But this expression will not work. Okay, let's test it. Let's say, for example, E is something, E max times cosine of kx minus omega t. And B is also something times cosine of plus. We're talking about the other one, kx plus omega t. If that's the case, this derivative here will give me a minus sine times k. Okay, I'm not writing the coefficients in here, of kx minus plus omega t. Okay, and this derivative in here will give me a minus times minus, which is a plus, times the derivative of omega times sine of omega t. We have a problem in here, sinus of kx plus omega t. We have a problem because here it's a strictly positive, that's the intensity. Here it's strictly positive, that's the intensity. Omega is positive, k is positive, everybody is positive, and I have an inconsistency. So the only way to solve that inconsistency, actually, if we follow the rigorous derivation, we will find that actually B and E will be out of phase when the wave is traveling to the left. Namely, when a right wave, yes, we drew it correctly last time, so there was no problem with its shape. So if this was traveling to this direction, and this were the electric field, the magnetic field also will vanish in the same point and maximize in the same point. So this is for one that is traveling to the right, this way. If I were to draw the same wave now, for one that is traveling this way, so this is the x-axis is still pointing this way, okay? This is not the x-axis. So again, the wave in the x direction is going to be for the electric field is going to go that way, but the wave for the magnetic field, now in order to satisfy Maxwell's equations, it has to go in the opposite. In other words, when the other one is negative, when this is positive, the electric field, the magnetic field is negative. When the electric field is negative, this one is positive. Okay, so I'm hoping that you see that, and it's straightforward from Maxwell's equations. So a right traveling wave will have to have the negative sign to compensate for the negative sign for the B field, and now everything works the same. So, and why do I say that? Why do we care about that? We care about that when we're talking about reflected waves. Because if this wave is moving and hits a surface, a shiny surface, or a metal, for example, it's going to bounce off of it. Well, the electric field will, because of the fact that there is no electric, let's say, for example, this is a conducting material. Conducting material has no electric field inside of it. So if a wave in here in the electric field comes in, when it bounces, it has to flip so that it cancels the electric field in that region. So this is the reflected wave now. So it's going to be like this. Okay? Because again, any motion of the charges in there will make it to compensate for, remember the stuff we talked about when we did conductors. So the wave will actually be flipped, whereas that of the magnetic field, so the one that is traveling to this direction, is exactly the way I drew it. Now for the magnetic field, let me go back to the incoming wave and try to draw the incoming with a different color. So this is the wave that came in. So it was in phase with its own electric field. Now, when it bounces back, it needs to be out of phase with the reflected one. So it needs to be in a different direction with the respect to the reflected one. So this is its phase, because this one is, actually, I'm sorry. This is, let me try to see it, how it works in here. So it was positive. This is negative now. So when this one becomes negative, this one is going to move in the opposite direction. So let me basically do the math. It's much easier, okay? And I'm going to talk about the standing waves in here, okay? Quickly. The standing waves is I'm a region of space where the wave is trapped. So basically, it bounces off of the wall, Goes back once, it bounces off of the wall, and going back, and it's like a cavity. They call them cavities, but a good example is a microwave oven. Microwave oven is a good example, okay? So if we take a microwave oven, the waves are trapped between the boundaries of the microwave itself. So in this case, what I have for the electric field is the electric field, which is a combination of the one that went to the right and the one that came to the left. So it's going to be an Emax times the one that traveled to the left. It's going to have the following phase: cosine kx minus omega t. When it bounces back, it's going to flip signs. So it's not going to stay with a positive cosine. It's going to be a minus cosine kx minus omega t. So that's what happened to that of the electric field. Now a different story is happening for the magnetic field. The magnetic field B, again, the one that went and hit the wall has the same phase: cosine kx minus omega t. When it bounces off of the wall, this one is a minus, the other one will have a positive, because it's going to have the opposite direction of its component in order to satisfy Maxwell's equations. So it's going to be a positive cosine of kx minus omega plus omega t. I'm sorry, this is the reflected. This is the one that is coming back. So this is traveling to the right, this is traveling to the left. This is again for the electric field. One is traveling to the right and one is traveling to the left. So basically, we have to deal with this algebra from trig classes. There is an identity in trig that says cosine of an angle plus or minus. This angle is a cosine of the first angle, cosine of the second angle, minus plus. If it's a plus, it's a minus here. And if it's a minus here, it's a plus there. Sine alpha cosine beta. If we do that and do the algebra here for the electric field, it's a cos minus cos. Cos of this two arguments minus cos of that argument. So let's find that of the electric field first. It's cos of kx minus omega t minus, because it's reflected now, cosine of kx plus omega t. This is cos cos. Kx cos omega t, using that identity. I have a minus in here, so it's going to be plus sine kx sine omega t. This is minus now, a big minus operation. Cos cos, again. The expression has a plus in it. And the trig identity, if it's a plus, you need to use a minus. So I will have a minus in here. But don't forget I'm subtracting that quantity. So the minus will ensure it at the end to flip back to positive. In other words, the one coming from the electric field, these two terms will cancel for the electric field, and this will add up. So for the electric field, the first term is going to have twice sine of cosine of sine of kx sine of omega t. That's one term. That's for the electric field. So the first term in here will give me 2 Emax times the product of the sine of kx and sine of omega t. Now I need to do the same thing in here, except I have a plus in here. So it's the same terms, except I'm adding them now. So for the magnetic field now, it's a cosine, again, of kx minus omega t, plus cosine of kx plus omega t. So the first term, it's cos cos. Cos kx cos omega t. Minus becomes a plus. Sine kx sine omega t. The second term now, plus cos kx cos omega t, minus, because I have a plus in here, so it's going to be a minus from the trig identity, sine kx sine omega t. Well, these two terms now cancel for the magnetic field. And I'm left with 2 times cos of kx, cos of omega t. So basically, the standing waves that form in this case is going to be the sum of these two terms. So for the electric field, it's going to be just the sum of the two. I'm sorry, I wrote this thing as a vector and I did not write my vectors, or something that is not good. So I need to pay attention to what I'm writing in here. So remember, this is happening in the y direction. That's why. So this is happening in the y direction, and this is happening in the z direction. So in the y direction for the electric field, so this is the y direction now for the electric field. If you want to write it that this way, it's 2 Emax times the products of the sines. Sine of kx, sine of ky. I mean sine of omega t. For the magnetic field, it's all happening in the z direction. It's again 2b max. Now the product of the cosine of kx, cosine of omega t. This is what's going on. At x equal to 0, if we take one of the sides of the microwave, the electric field cancels, as we expected. If I go to the other side of the microwave and require that this is a standing wave, that too, E is cancelled. So the electric field vanishes at the ends of the microwave. But the magnetic field doesn't, because of the fact that omega kx in here is going to be max for x equal to 0, it's 1. And L there also, for the when I impose a condition in here that kx is equal to, so if the microwave have a width L, you guys did standing waves, didn't you, in physics 1 for the string? And actually you did the lab too. Yes? Yes or no? Yes, okay, so that's the same idea, except I have 2 fields now to deal with. So again, the condition that these are standing waves and I have resonance in this case is the fact that the sine itself cancel, and the sine will cancel when kx is multiples of at L basically, are multiples of pi basically. Anything that is pi or 2 pi or 3 pi makes that work. So k times L is equal to pi, and k is 2 pi over lambda. So 2 pi over lambda is times L is equal to pi. Cancel the pi from both sides, and the wavelength in here of the standing waves that form is going to be what? Lambda is equal to 2L. So I can have basically, if I can have a 2 L's, I can have 4 L's, I can have different standing waves. Did I do the algebra correction here? Yes, okay. So these are called antinodes. That's basically where the wave cancels, where the standing waves could cancel. So basically it looks like this, okay? Or like this, okay? The same thing, but kx doesn't, cosine in here doesn't vanish. It vanishes actually where the electric field maximum is maximum, the magnetic field is minimum. Because again, the points that makes this one vanish makes this one maximum, and vice versa. So these two now, they are not in phase completely at all. They are actually quarter of wavelength out of phase. So in a standing wave, the story is a little bit more different, and that's basically a typical number that you have in here. So in here, for example, a microwave oven of, I think there is something, do I have it in here correct in here? 2 pi over lambda, that's k. And k times L, yeah, that's correct. Okay, that is correct. The math is correct, okay? So that's basically the wavelength is proportional to basically the number. Of course, I have other conditions. This is not the only standing wave I have. Anything plus 2 pi basically would make this one work. So anything plus 2 pi or n pi. In general, I have n pi. So there is actually an n in here. So the actual number in here, lambda, is going to be this number divided by n. Okay, where n is any integer you like. Okay, so you'll have standing waves abound. So that's basically why we use a microwave. What microwave is a few centimeters wide, and the wavelengths is of the same order of magnitude, and this is actually the microwave region that makes the molecules of water vibrate. And that's really the point behind this idea, is that you use this one for to heat water, because that's basically what most of the food is. It's mainly water. So the water vibrates, except that there is a problem with a microwave. And that is there are points in the microwave that the electric field vanishes. Those are the nodes, not just in the ends where the electric field vanishes. It vanishes also somewhere where there are nodes in there. So the solution for that is people thought, okay, if I have the entire food is sitting on a plate, for example, and that plate spins, so that makes sure then that those points are for the entire plate, basically, that you're cooking. Not a single point stays cold. The entire water basically will go and move around in the microwave, and now all of a sudden you have something to use it to cook. All you have to do is just make this water molecules move fast enough, and when they do, of course, that's heat. That's something that you're going to take in physics 3 with thermodynamics, and you understand that heat is actually or temperature is actually proportional to the kinetic energy of the gas or the liquid in this case. Okay. With the standing waves, everything we're supposed to cover in terms of content, we've covered it in this class. We did optics. We talked about geometrical optics when we started. We did wave optics after that. And then we went into the electric field. We did, first of all, Coulomb's law. We discovered the electrical field, basically properties, that there is some charges and things like that, define the electric field, start working with that. We discovered Gauss's law, and then we moved on after that. We found the electrical potential. We used that to do a lot of interesting stuff with the resistors, basically, that we defined that they have peculiar properties in terms that they resist those are special conductors, basically some of the properties of conductors. We did circuits after that, DC circuits. And then we discovered after that currents actually that are moving in charges, they create magnetic fields. So this magnetic field turn out to have related to the electric currents that generates them. And later on, basically, we discovered the other way around, that if you have a magnetic field changing with time, that is actually going to induce currents. And now we have AC circuits. We did AC circuits. We worked with a lot of different devices, motors, generators, and all kinds of things using these ideas. And then we put them all together in terms of Maxwell's equations, and we learned everything we know in physics so far. F equals to ma, Lorentz force, and Maxwell's equations that basically state the following. If you have distribution of charges, you really have an electric field. If monopoles do not exist, that's why the magnetic field never diverges. So the divergence of the electric field is proportional to the source that created it. And then we said that Mr. Ampere and Maxwell corrected later on by, Mr. Ampere later on corrected by Mr. Maxwell, state that a magnetic field circulates around currents that generates it, or in the case of, in general case also, a changing electric field will also generate a circulating magnetic field. And finally, that there is a new type of electric field that is generated due to changing flux of the magnetic field, and that is actually circulating also a magnetic field. And that magnetic field, we took it in the free space, basically, away from any source, and we found basically this electromagnetic waves that they have these properties. And it turns out that light, we learned way back. We said that it's made of particles moving around. We said, no, wait a minute, it's not particle. And then we said, actually, now it is a wave, actually. So, and this is the interpretation for it. You're in for more surprises when you take physics 3, and you will learn that light actually is not a wave, it's actually a particle, and that is a photon. And actually light at the end of the day will behave both as a wave and as a particle. So this is your course. This is everything. Remember this story. You're going to tell in your kids, okay? Thank you, Aaron. Remember, you're going to tell your kids later on. If somebody tells you what you learned in physics 2, this is what I want you to remember. This is what I want you to tell them. What I just said, okay? I'm hoping that somehow you can remember that. Because at the end, you're not going to remember problem 71 from chapter 32 or from chapter 27 or something. And if you ever encounter it in your life, there is actually good resources for you, including Google or some other places to solve that. But what guides you towards solving these problems and actually in your life as an engineer or as a scientist is this big picture. The big picture is very important. Okay, it's more important than anything else. That is actually what knowledge is. That's what you're going to retain at the end of the day. Okay? Any questions? When I reach this point of the class, I really feel happy, but I really feel sad too, because I feel like a good story came to an ending, a beautiful story came to an ending. So it's really with emotions when I reach this point. Okay, I remember the day when we met also, and I told you exactly where we're supposed to be, and that is exactly where I hope that we're what we went to in terms of Maxwell's equations. You guys remember that discussion we had in the lab? Yes? Okay, good. Okay, guys. It was my pleasure. We still have 3 things to do. We still have exam 5, which is next week. I'm going to rely on you doing reviews. And if you need me to be here on Tuesday, I'm going to be here on Tuesday for you guys. Yeah, they are crazy, the equations, but they're fun, hopefully. If you put it in these terms, Julian, they're fun, okay? Ignore those complicated looking equations. So we have exam 5 Thursday. If you want me to be present on the Tuesday, I will be, but I hope to have 2 or 3 people in the audience so that we have an interesting discussion. Also, we have the quiz, the post test, which I'm going to post sometime next week. Do not forget it, okay? That is for extra credit for exam 5. And I still owe you the extra credit from exam 1. I did not grade that, and especially now since I don't have Scantron, I'm going to do it by hand. Okay, so that's a quiz. That's the only Scantrons we do. That's the only multiple choices we're going to have in this class. Okay? Then we still have a final, which is the Tuesday of, not this coming Tuesday, the Tuesday after. So that's basically in a nutshell. You still owe me 3 assignments, basically, in addition to these exams. This sound good?
Sounds good.
Okay. Okay, guys. I'll please take care, okay, and stay safe. No matter what they say, even if they say you can leave with caution, okay? And I'll contact you guys during the week, okay? Tim.
Thank you, DJ. See you later.
Bye. Thank you, Jillian, John, Winter, Gareth, Andrew, Jonathan, Sophia, Aaron, and I know that, what's his name? I forgot the name now. Gino is not here, but hopefully he's going to be good too. Thank you, Jackson. Okay. See you guys. Bye.
Bye.
Okay.